Okay, so we are going to be talking about the behavior of gases today, and you need to be able to identify 4 ways to measure gases. And then after that, you'll be able to apply a formula to determine the pressure or volume of a gas. So, first of all, talking about gases, they're like fluids, they have low density, they are highly compressible, right? You can squeeze them. They completely fill their container and they actually exert pressure. So these are facts, but how do we know that that is true? All right. This is called kinetic molecular theory, which is the theory that explains the physical properties of gases by describing the behavior of atomic particles. So if we want to show why those 5 things are true, we need to look at the atomic particles. So the kinetic molecular theory states that gas particles do not attract or repel each other. And I have to apologize, this was a PowerPoint, so you can't, the graphics are off. But basically, it's just showing that they do not attract or repel each other. Also, there are much smaller distances between them, or they're much smaller than the distances. So you have your little gas particles, and the distances between them are enormous compared to the size of the gas particles. They are in constant, random, rapid motion. They have the same average kinetic energy at a given temperature. And the 2 scales that we'll be using to measure them are Kelvin, which is absolute, and Celsius, the centigrade scale. All right. The differences between these are just that in Kelvin, 0 degrees Kelvin is called absolute zero, and that's actually minus 273 degrees Celsius. So what that means is that at 273 degrees Kelvin, that is 0 degrees Celsius. All right. And that's where water freezes. So water freezes at 0 degrees Celsius, which we're pretty familiar with that. And what that is that is 270 degrees Kelvin, or 273 kelvins. And water boils at 100 degrees Celsius, and that is 373 kelvins. And so what's interesting about that is, like, notice a Kelvin degree is the same as a Celsius degree. So when they collide, these gas particles, they do not lose energy. They just bounce right off each other. Nothing, and so that's important to understand how gases, the reason why gases act the way they do. All right, so all gases have the same average kinetic energy at a given temperature. No energy is lost when gas particles collide with each other or when they collide with the container. And this is different than we're used to, because we're used to energy being transferred. If you crash into another car, you come to a complete stop. All right. Particles are not going to do that. They will this is called an elastic collision, and it just bounces back the other way, exactly in the opposite direction. So you want to be able to draw these 5 points of kinetic molecular theory. All right, so try to remember those 5 points and then draw a picture of what that would look like. All right, so the next thing we need to be able to do is measure gases. So we have volume, which in the unit for that, we'd say we have milliliters or liters or cubic decimeters. Um, Another unit, we can measure the temperature of gas, and we would do that with degrees Celsius or kelvins. And like we said, absolute zero for kelvins is actually negative 273 degrees Celsius, and 0 degrees Celsius is 273 degrees. So there's a difference of 273 degrees, basically. And Fahrenheit is just totally different, so we're not even going to talk about Fahrenheit. Pressure, the units would be atmospheres, kilopascals, and millimeters of mercury. All right, so we talk about pressure, you have to measure your tire pressure. If you're driving a car, it's very important that you have the correct tire pressure, or you can have an accident while you're driving. Little n is the number of gas particles that you have. And that's, again, remember the old mole. We're talking about 1 mole being 6.02 times 10 to the 23. All right, so how do we measure gases? We can measure the volume of gas, right? How much space it fills up. And these would be the units. We can measure the temperature of the gas. And we always do that in kelvins. All right, so when you're measuring volume, you would use milliliters or liters, or a cubic decimeter, which is 1 liter, or a cubic centimeter, which is 1 milliliter. But in temperature wise, you always use Kelvin. So if you have degrees Celsius, you would just add 273 to that. Then that would tell you how many kelvins you have, the temperature in kelvins. Pressure, you have 4 units for pressure. The conversions there would be 1 atmosphere is 101.3 kilopascals, which is 760 millimeters of mercury, which is equal to 760 torrs. So that is something you need to remember. And how do you remember that? By doing a bunch of problems. And then the number of gas particles that you have that in moles would be that little n. All right, so the unit there is moles. So you have these 4 factors that determine how the behavior is, how your gas is going to behave. And you saw that when you were working with that FET lab. When you change the temperature, the gas acts differently. When you change the volume, the gas acts differently. Change the pressure, change the number of particles, it changes how the gas acts. So we're going to be solving problems, and we have a little system here. Similar to when we were doing dimensional analysis, you always start with what you're given. And then you focus on what is unknown. What are you trying to find? The nice thing about this is that you will have a formula. And so you use that formula to write an equation. You substitute into the formula, and then you solve for your unknown. So you just use your algebra. And this forms a little acronym called GUESS. All right. So Boyle's law is if the temperature is constant, the pressure and the volume of the gas are going to vary inversely. That means if one goes up, all right, if the pressure is increasing, I'm trying to use my pen, then the volume is decreasing. Okay, I need to hold this straight. That's my problem. All right. So that's an inverse variation. One goes up and the other goes down. And how that looks would be, that means if you multiply them together, you get a constant. All right, you always get the same number. And this number is going to be equal to this number. And so it makes sense. If I increase the pressure here, then I have to decrease the volume here so that I get the same number over here. All right, if you increase the pressure, you're going to decrease the volume. That's how you keep this constant. That's how you keep this as the same number. All right, so let's look at that in action. Actually, we're just going to practice problems here. You can do that on your own. So what this would look like graphically is, it's not a straight line. It is this curved line. That's an inverse relationship. So what that means is as the volume is increasing, right? The volume is increasing here. Notice the pressure is decreasing. Okay. That is an inverse relationship. If I increase the volume, I lower the pressure. Okay, and we know that. That kind of makes sense. The pressure is how the particles are hitting against the sides. Well, if there's more room, then there's less pressure. They're all spread out. All right, so what kind of problems are we going to solve here? So we have a sample of gas, all right, so that's important to know. So we're looking at our gas laws. I've got 523 milliliters at 1 atmosphere, and I'm going to increase it to 1.97 atmosphere. So I want to know the new volume. So what am I given? I'm given pressure, right? I'm given the pressure. All right, my first pressure is 1 atmosphere, and my second pressure is 1.97 atmosphere. So the pressure went up. I increased the pressure. So that means my volume's got to go down. All right. Well, let's see. Let's use this formula. The new volume is my unknown. All right. I don't know this. I have, with this first pressure, I did have a first initial volume, and that was 523 milliliters. Okay. So I know my equation is, since this is Boyle's law, and I know that it's inverse. So PV equals PV. All right, now I'm going to substitute what I've got. And so I've got 1 atmosphere times 523 milliliters is going to equal 1.97 atmospheres times V. I don't know this volume, okay? So how do I get this volume by itself? Well, these are being multiplied, so I'm going to divide both sides by 1.97 because then that goes away. So I get my second volume is going to be this divided. All right, so I'm going to type this in here. I've got 523. I guess I could put the 1, but we know 1 times something is that something. So 1 1, and then I've got parentheses, can't see it, 523. And then that is going to be divided by 1.97. All right. And so that gives me 265.5. All right, 265.5 for my new volume over here. 265.5, and then that would be milliliters. All right. Right, because this was in milliliters, so this is going to be in milliliters. So I was expecting, right, my pressure went up, so my volume is supposed to go down. Did it go down? Yeah, it went almost cut in half, and that makes sense because I basically doubled my pressure, so I cut my volume in half. All right, so that looks good. That makes sense. All right, so now we have a sample of gas. Let me scooch this over so I can read it. Oops. Should close all that other stuff. I'll just move it down here. There we go. All right, so sample of gas had an initial volume, right? So initial means beginning volume of 15 liters. So my beginning volume is 15 liters. And then I have a final volume, right? So that's my final volume is 17 liters. So my volume went up, right? So my pressure is going to go down. Well, let's see. So my initial pressure was 1.5. So my initial pressure is 1.5 kilopascals. All right. So now it says to find the final pressure. So that's my unknown. What's the final pressure? I don't know. I do know that they're inversely related. So I know volume times pressure equals, or pressure times volume. And I can switch that order around because it's commutative, right? If you're multiplying, no worries. So now I'm going to substitute in what I've got. So my first pressure and volume were 1.5 times 15. And I don't know my second pressure, but I do know the volume was 17, right? So again, I have time. My variable that I'm trying to find is by itself here. It's being multiplied by the 17. So I'm going to divide by 17 because that's 1. All right, and so I get my second pressure is going to equal whatever this is. So I'm going to type this in over here, 1.5. 1.5 times 15. Divided by the 17. And that gives me a new pressure of 1.3. Since this was in just two significant digits, I'll just make that two significant digits. So 1.3, and this is kilopascals, so this would be kilopascals. And that would be my final answer. All right. So that is Boyle's law. Boyle's law had to do with pressure and volume. Charles' law is talking, now the pressure is constant, we're talking about volume and temperature. All right. So, oops, I didn't bring that down here. All right. So volume and temperature. And this is different too. It's directly related. All right. right? So that means when the volume goes up, the temperature goes up, all right? If you heat up that gas, or if you if you heat up the gas, then it's going to spread out. The molecules spread out. You increase the volume, all right? Or if I spread out the gas, if I lower the pressure and let the volume, well, if I increase the volume, that is going to spread out the molecules, and so that is a lower kinetic energy. All right, if I decrease the volume, all right, that means the molecules are closer together. That means they're going to have a higher kinetic energy. They're going to have a lower kinetic energy. So if you decrease the volume, so your molecules are, squished in together, that means you have lower temperature. So Charles' law is a direct relationship. Actually, I like this one better because my temperature, if I increase the temperature, so if I heat up the gas, that is also going to make the molecules spread out, and so I get a bigger volume. Okay, that's easier to explain. So the temperature is going up and the volume's going up, and notice that is a straight line. That's a direct relationship. Okay. All right, that's linear. All right, so one thing that is very important is the temperature must be Kelvin. And to get to Kelvin from Celsius, you just add 273. All right, so we have a balloon, it's inflated, so we're talking about volume, and we're talking about temperature, so we're thinking Charles's law. So what am I given? I'm giving this volume. My first initial volume is 665 milliliters. My initial temperature with that is 300 kelvins. So that's good. It's already in kelvins. If it's a really high temperature, it's probably kelvins. And then we put it in an ice bath, and so the temperature goes down. I have a new temperature. It is 194.5 kelvins. So the temperature went down, so we would expect, since it's a direct relationship, the volume's going to go down, right? If I cool it off, then all the molecules are going to go together. They'll stick together and be close. And so that would be, we're expecting to have a new, smaller volume. That's my unknown. All right, and now I have my equation. I have Charles' law. So I know that my volume and my temperature are directly related. So you divide them, right? If they're inverse, you multiply. Direct, you divide. And notice direct and divide both start with T. So I have my first volume and temperature, and I want that to be equal to my second volume and temperature, but divided this time. Okay, so this is Charles's law, and now you just substitute what you've got. So my initial volume was 665. My initial temperature was 300 kelvins. I'm going to leave off the units because I'm doing algebra here. And now my volume, I don't know the second volume, but I do know the temperature. My new temperature was 194.5. Okay, so notice I have both the volumes together and I have the temperatures together. Now, to solve this proportion, this is a proportion, right? You have two fractions equal. The easiest thing to do is to cross multiply. So I'm going to multiply this times this. All right, so 665 times 194.5 is equal to this times that, which is equal to 300 V. All right, now the V is, my unknown is over here, stuck to the 300. That means it's multiplied. So I'm going to do the opposite. I'm going to divide. So divide by 300. All right, so now I have my volume is equal to this. 665 times 194. So I'll put that in here. I don't know why I'm doing this in the dark. 665 times 194.5, and then it's divided by oops, 300. And you get 431.1. All right, so 431, oops, 431.1 will be my new volume. And now I put in the units. Now it's very important at the end that you have your units. So I had 665 milliliters. So this would be 431.1 milliliters is my new volume. All right, very good. So this is just basic Algebra 1, no big deal. You just need to read the question carefully. Look at what you're given. I've got a gas, so I'm going to be thinking, okay, gas laws. I've got a temperature, so I'm thinking Charles' law. And I've got Celsius, so I'm thinking, oh, I've got to convert that to Kelvin. That's no big deal. I'm just going to take my 15 plus 273, and that would be 288 kelvins, okay? So I'm given a temperature. My first temperature is 288 Kelvin. All right, and the volume that goes with that gas is that the volume there is 10.2 liters. All right, so I've got a temperature and I've got a volume. And then now I also, it says if the volume is changed to this, so I have a new volume, right? So my new volume is 16 liters. So my volume went up, right? I increased the volume. Well, remember, that means I'm going to increase the temperature. Temperature goes up. If the molecules are all spread out, that means the temperature is higher. So my new temperature, right, it says what is the new temperature? My new temperature is the unknown. That's going to be higher than 288 Kelvin. And then I know Charles' law, temperature and volume are directly related, so I'm going to divide. I've got volume divided by temperature. Volume is to temperature as volume is to temperature. All right, it's a direct relationship. And then now I just substitute in what I've got. So my volumes are, I've got 10.2 liters at, oh, this should be one. Right, these should go together. This volume and this temperature should go together. So at 288, and the volume, my new volume was 16, and I didn't, so, and I'm trying to figure out, oops, the new temperature. Why am I struggling on this? I'm trying to find out my new temperature. That's a T. All right, so to solve, I'm just going to cross multiply. So I've got 10.2 times temp T equals 288 times 16, right? And now my T, I've got 10.2 times T, so I'm going to divide by 10.2, and that goes away. Divide by 10.2. So that means that this temperature, my new temperature, is going to be the 288 times 16 divided by 10.2. And that is 451.8. Right, I'm going to round up there. And my temperature is, and that's always going to be in kelvins. And so I was expecting the temperature would go up, and my answer is bigger. Right, it went from 288 to 451. So I know I probably did that right. All right. So very good. That is the Boyle's Law and Charles Law. All right, and so now we've got the 5 points of the molecular theory. Can you remember what those are? Going back to the very beginning. 5 points of molecular theory. What was that? Let's see if we can draw, how could we draw a picture of that? Well, number one, they do not attract or repel. So here's a particle, here's a particle. There is like attraction, and then this says no, they do not attract. Remember, repel means they're like going opposite each other, like magnets that you can't, when you try to squeeze them together and they won't go together, that's repel. So they don't repel. They're just bouncing around. All right, the gas particles, they don't have a charge. They're much smaller than the distances between them, right? So you have a little particle, right? And a really big distance between all of your particles. See how spread out they are? Okay. Number three, they're in constant, random, rapid motion. So they just move straight. They're not bending. They're just going straight randomly. And they never stop. They have the average kinetic, same average kinetic energy at a given temperature. Kinetic molecular theory, they don't lose energy when they collide with each other. All right, so here's a drawing of that. All right, so they hit the container, and you know that they just bounce right off. All right, those are the 5 laws that you want to remember about when you talk about how gases are going to act. All right, those are the things you want to keep in mind. And we have Boyle's Law and Charles' Law, and then you can actually combine these together. And we'll talk about that next.